Welcome back to Robotics Mechatronics System Design course. We will continue with the Lecture 6 Air Preparation and Vacuum. We finished the air preparation in the part 1 of the lecture, and we are going to discuss the vacuum part, which is basically part 2 of Lecture 6. So in this graph, you could see the vacuum or the air pressure. 1 atmosphere is the atmosphere pressure. Okay, so 1 atmosphere is equal to 1 bar and is equal to 100 kilopascal, which is a pressure of the atmosphere or the pressure of atmosphere at sea level. So now we have this P0 as atmosphere pressure. If the pressure increases above P0, we will have PG, which is the gauge pressure. So when the gauge pressure is positive, we have absolute pressure or PA of more than P0. So absolute pressure is equal to pressure of atmosphere plus pressure of gauge. Why do we call it gauge pressure? Because in many gauges, they show relative pressure to the pressure of atmosphere. So at the beginning, the PG is 0, and once the pressure increases, then the PG will increase. So when the PG is positive, we have a pressure more than pressure of atmosphere. So then we could call that pressure compressed air. Okay, compressed air. So compressed air is when we have PG of positive or PA more than P0. However, we could have gauge pressure of less than 0 or negative gauge pressure, and we will call that vacuum air. So in this case, the absolute pressure will be less than P0 or less than atmosphere pressure. We cannot achieve absolute pressure of 0. It's very tough to reach absolute pressure of 0. So when we say we have vacuum, it means that we have a pressure which is less than pressure of atmosphere, or PG is negative. Okay, so how could we create vacuum in pneumatic systems? A very common practice is to use Venturi. This is Venturi. This is a cross section of Venturi. At the intel, we have a fixed or constant cross-sectional area. At the middle, the cross-sectional area will decrease, and then at the outlet, the cross-sectional area also will increase. So you see that what's happening, and at the middle we have a neck. So this is Venturi. We have an airflow from the inlet to outlet. Okay, so we have an inlet and we have an outlet. This is a symbol of a Venturi. 1 is inlet and 3 is outlet. Based on continuity equation in fluid mechanics, AV is constant. A is cross-sectional area and V is velocity of air or airflow. So A1, V1, this is a first section or one section, and the second section or two section is the one exactly at the neck of the venturi at the middle. So A1 V1 is equal to A2 V2. So when the cross section decreases, the velocity should increase. So here we have higher velocity than the inlet. Based on Bernoulli equation, and in fluid mechanics, they drive Bernoulli equation is based on conservation of energy. P1 divided by gamma plus V1 square divided by 2G plus Z1 is equal to P2 divided by gamma plus V2 square divided by 2G plus Z2. P is pressure, and gamma is a specific weight of air. This one is a potential energy. V is velocity and G is acceleration of gravity, and this term is a kinetic energy. This term is kinetic energy, and Z1 is basically height, okay, and this one is also potential energy due to gravity. So Z1 and Z2 for venturi, which is a horizontal venturi, is the same. Okay, so Z doesn't have effect in this equation, and since based on the continuity equation we know that V2 is more than V1, then we could conclude based on the Bernoulli equation that P2 is less than P1. So pressure here at this section is less than the pressure at the input. So if we could design a proper cross section, and if we could fit the inlet with a proper pressure, we could achieve a pressure P2, which is the absolute pressure. Okay, so P here is the absolute pressure. We could achieve a P2 which is less than the pressure of atmosphere, and that could create a suction. Okay, so here let's say this port is connected to the atmosphere, then it will create a suction and we will have an airflow from the atmosphere to the neck of the venturi. So that's why in the symbol we have a suction cup here. So the suction cup, at the suction cup we will have a suction, and we could have pick and place by the suction cup. Okay, so here is an industrial sample of a venturi. You could see the symbol here. We have input P, we have a output R, and we have a suction at a V or at the port 2. Okay, so here is the input, here is the output. You see that we have a muffler here to reduce the noise and sound of the air, okay, because it's connected to the atmosphere, and here at this port we have suction. Okay, so we could make a circuit in Festofluid Sim. I strongly recommend you to simulate the circuit in first of all lighting by yourself. So see what's happening here. We have a 2x2 directional valve. So this 2x2 could be a solenoid that just opens and closes the basically opening to the port 1 of the Venturi. This is a port 1 of the Venturi, and this is port 3 of the Venturi. You see, this is a muffler to basically reduces the noise of exhaustion to the air. And here we have suction. This valve is a one-way non-return valve, and this one is a filter. This is an air filter, and here we have a suction cup. It is very common to have a filter. We have it on distribution station of MPS 500, and the reason is because we are sucking air from the atmosphere, and in most cases we have some parts, because the suction cup is going to pick a part. So let's say that part is wood or a metal which has lots of dusts, and those dusts could be suctioned into the pneumatic circuit. We don't want that happen, so it's very common to have an air filter to reduces any dusts and particles from the atmosphere or from those parts. So this is just a filter, and see what's happening now. Okay, now the directional valve is open, and we have a negative pressure at the Venturi, and now we have a suction. So air is flowing in this direction. And why do we have this non-return valve here? Because at the beginning we could have some leakage of the air from the Venturi to the suction cup. We don't want that happen, and that's why we basically have this non-return valve. Okay, so the suction, here we have a suction, and let's say this is a surface or plate or the part that we are going to basically to peak. So the part is peaked. Okay, so now this port is closed because the part is already peaked, and since the part is peaked and we have this non-return valve here, we have a negative pressure here. Okay, and now the pressure also will increase at the Venturi, and it will the non-return valve will close the pathway to the suction cup. Okay, now you see that we have a closed circuit. We don't have now any basically leakage of the air to the Venturi or to the atmosphere. Why we don't have any leakage of the air to the atmosphere? Because after we managed to suck the part by the suction cup, we could close also the directional valve. So once the directional valve is closed, we don't have any airflow here, so we won't waste air to the atmosphere. Plus this line or the circuit also is closed and includes a negative pressure or the vacuum pressure, and we don't have, let's say ideally we don't have any leakage of the air to the suction cup. So by having this type of circuits, we could manage basically we could manage or we could stop losing air to the atmosphere, so the compressor doesn't need to provide constantly air to the venturi, and we could have an optimized circuit in terms of the energy. This is a vacuum filter that we have on the MPS 500, and this is a symbol for that filter. If you watch videos again and look more carefully at the videos, you could see this part in the distribution station. Okay, it's just a filter to stop particles and dust coming into the pneumatic circuit. A vacuum switch. This is a vacuum switch that we have on a distribution station, and you see this is a symbol, and this is the basically the input or the pneumatic port to the vacuum switch or sensor. Okay, so the vacuum switch is type of a sensor which could measure negative pressure, negative gauge pressure, or vacuum pressure. So once we have a proper, or once we have reached a desired vacuum pressure, then the vacuum sensor will close the directional valve. Okay, so that directional valve that you have seen in the previous slides will be closed by the vacuum switch. And if the vacuum pressure drops, okay, then the vacuum switch again will turn on that directional 2x2 valve. Okay, because of course the circuit that I presented is the ideal one, but in a real system we could have some leakages of air from the atmosphere through the suction cup into the circuit. So the pressure of the vacuum pressure will drop, and the part basically will drop at the middle of the way. So we don't want that happen. So we need to measure the vacuum pressure, and once the vacuum pressure reaches to the desired one, the vacuum switch will stop flowing of the air into the venturi, or will shut the 2x2 directional valve. And when the vacuum pressure or the negative gauge pressure will drop to 0 or less than the desired threshold, then the vacuum switch will turn on the airflow to the venturi again to have suction. So this is the end of this session. I hope you guys managed to work on examples and homeworks, and I expect you to submit all of those examples and homeworks to Moodle by end of this week, and next week we will have a quiz. This is basically the end of pneumatic topic. Of course, we will have combination of pneumatic circuits and PLC in coming sessions, but the exclusive topic on pneumatic part is finished.